Hello, everyone. My name is Sina Sajjad Manesh, and I am a PhD student at the DIAB Research Institute and EPFL. I will be presenting our paper, Locally Private Graph Neural Networks, which is a joint work with my advisor, Daniel Gettiga-Press. In this work, the problem we address is actually learning graph neural networks, or GNNs, with no data privacy. So let me explain this problem with a motivational example. Consider that we have a social network server like Facebook, and this server wants to train a GNN over the graph of its users, the user-user relationship graph, which is actually public to the server. But to be able to train a better model, they kind of need to have richer initial node features through accessing users' personal data, like their phone sensor data or their health records or so on. So we have a server with a graph, but the nodes that may correspond to real human users have some sort of private node data that can be used as either features or labels or both. Now, the problem is how we can train this GNN that utilizes private node data in a privacy-preserving way. To address this problem, to preserve the privacy of nodes, we propose locally private GNNs based on local differential privacy. Our contributions include building a new privacy mechanism called the multi-bit mechanism for high-dimensional feature perturbation. We also propose a simple graph convolution-based layer called KProp for improving the accuracy of our estimations. And finally, we design a novel learning algorithm called DROP for learning with privatized labels. I will go through each of these during this talk. So before getting started, let me quickly review the concept of local differential privacy, or LDP. So in the local model of differential privacy, instead of collecting all the private data in a central location, each data holder perturbs their own data with a randomized mechanism and then sends the perturbed version to a central aggregator whose aim is to compute an aggregate function, such as mean, count, histogram, and so on. So this perturbation mechanism is designed in a way that the noise injected into the data would cancel out through the aggregation. Clearly, the mechanism we use must satisfy the LDP condition, which basically says that for any two inputs, x1 and x2, and for any output, the likelihood of getting the output with x1 should be roughly similar to the likelihood of getting the same output from x2. And this similarity is captured by this epsilon parameter, which is basically called the privacy budget or privacy cost. So now, getting back to our problem, learning GNNs with no data privacy, the question is why local DP could be useful to solve this problem? Why graph neural networks are amenable to local DP? Actually, the reason lies in the way graph neural networks work, the way they operate, which is quite different than other standard neural networks like CNNs. In graph neural networks, the goal is to learn a representation vector for each node, which then can be used in various downstream tasks like node classification. To do so, we usually start with a feature vector for every node, and then every GNN layer tries to generate a new vector for the nodes, basically by performing two steps. First, the aggregate step, and then the update step. So in the aggregate step, each node basically aggregates its neighbors' vectors with a permutation invariant function, like mean, sum, or max, and then gives this aggregated vector to the update function, which is basically a neural network to generate a new representation vector for the node. So now, if we think of the first aggregated step as the data aggregator in the LDP scenario, and different nodes as the data holders, we can actually perturb node features at the node side, at the user side, and send them to the server to be fed into the GNN. And we can actually hope that the injected noise would cancel out in the first aggregated step. But for this, we have some challenges that we need to deal with. So the first challenge is that usually nodes or users have a lot of features. So we have a high dimensional feature vector for each node. And if we set to perturb all the features, either we have to spend a lot of privacy budget or inject a lot of noise to get a reasonable privacy. So to overcome this issue, we propose the multi-bit mechanism, which we specifically designed for effective privatizing of high-dimensional data. Basically, our mechanism consists of two components, the encoder and the rectifier. The encoder is run by each node at user side and it basically perturbs a random subset of the features, compresses the result, and sends it to the server. But as this process introduces a bias into the perturbed features, we run the rectifier at the server side to decompress and debias the encoder's output, which basically gives us an unbiased perturbed features for the GNN. You can refer to our paper for additional details about our mechanism. Another serious issue that we face with is that many real-world graphs are actually scale-free networks, which means that for many nodes in the graph, we have only a few number of neighbors. But we actually need the nodes to have many neighbors so that the injected noise into the features could cancel out during aggregation. But it would be hardly possible with only a few neighbors. Our solution to this problem is to expand the neighborhood around each node to include not only its immediate neighbors, but further nodes as well. Well, what we do is that instead of having a single aggregated step at the beginning, we apply k consecutive linear aggregated steps without any nonlinearity in between to keep the result unbiased. This way, we can actually increase the receptive field of every node to its k-hub neighbors. We call these k aggregations the KProp layer, which can then be prepended to any GNN architecture independently. Now, we need some labels to train the GNN. Now, if the labels are also private, like features, we also have to use an LDP mechanism to perturb them. For this, we basically use the randomized response mechanism, which is a classic mechanism for privatizing categorical data. The randomized response actually keeps the true labels with some probability that depends on the privacy budget and the total number of classes, or otherwise flips the label to another random one. In our method, each labeled node basically applies randomized response on its label and then sends the outcome to the server. Clearly now, if we simply train the GNN with these noisy labels, the model overfits the noise and then generalizes very poorly. So we kind of need a way to denoise the labels and recover clean labels. So for this purpose, we also use KProp for denoising labels in the same way that we did for features. The intuition here is that usually in real graphs, neighboring nodes tend to have similar labels. And thus one can estimate the label of a node by just looking at the label of its neighbors and aggregating them. But again, to have a good estimation, we need to aggregate over many neighbors. So KProp could be useful in this case as well. So at the server side, we apply KProp on the privatized labels to recover true labels. Note that this label KProp is totally independent of the feature KProp and could have different number of iterations. Now, a big question is how we can actually find the best KProp parameter or any other hyperparameters without having clean labels. If we choose a low K for KProp, the noise remains in the output and decreases the accuracy, while if we choose a high K, then it could lead to oversmoothing and again, low accuracy. Clearly, if we had some clean labels, we could simply test different hyperparameters to train the model, and then just use the clean labels to assess the classification accuracy, and then pick the ones that perform best. But because of privacy reasons, it would be more realistic to assume that the server does not have any clean data for validation. Well, normally in deep learning, validation data is used for two things: hyperparameter selection and preventing overfitting by early stopping. But without clean validation data, neither of these two can be done reliably. So we kind of need to find alternative methods. So for the first thing that we do to prevent overfitting is that if we train the model with the recovered labels, I mean, those coming out from KProp, then our GNN will eventually be a predictor for the recovered labels. But we actually want our model to be a predictor for the true labels. So in order to enforce this, we apply the same process that we did on true labels on the predictions as well. In other words, what we did was that we first applied randomized response on the labels and then KProp to get recovered labels. So now we apply the same process, I mean, randomized response and KProp to the GNN's output to manually make a predictor for recovered labels. This way, we can actually force the base GNN to become a predictor for the true labels. We then detach this module from the GNN after training. Note that here, the KProp on predictions is identical to the KProp to the labeled KProp in terms of the number of iterations. But this approach is not enough on its own to prevent overfitting, because if the KProp parameter is low for the label noise, it cannot recover the labels efficiently, and thus the GNN again overfits the noise generated by a randomized response. So to overcome this, we actually exploit the fact that the randomized response mechanism gives us an expected label accuracy. In fact, we know that randomized response keeps the true labels with a certain probability, and this probability is actually the same as the expected label accuracy. So what we do is that during training, we calculate an accuracy by comparing the GNN's predictions with noisy labels coming from randomized response, and we stop the training if this accuracy goes beyond the expected label accuracy, because this is a signal that our model is overfitting to the noisy labels, so it can predict them with a higher accuracy than what is expected. And finally, for model selection and hyperparameter optimization, we use the so-called forward correction loss, which is calculated between the predictions coming from randomized response and noisy labels. We actually use this loss function, as it has been shown in the literature, to be an unbiased estimator for the true loss, namely the loss between GNN's predictions and true labels. We call this entire algorithm labeled denoising with propagation, or simply drop. Okay, so now let's go to the experiments. Our learning task is node classification, and for this, we use a two-layer graph neural network as the backbone model, and by default, we're going to use GraphSage, which is one of the standard and widely used GNN architectures. For KProp, we use the linear aggregator from graph convolutional networks. We use 4 different datasets. Quora and PubMed are citation networks with nodes as documents and links as citations. Facebook and Last.fm are 2 social network datasets. In Facebook, nodes are Facebook pages and the links are mutual likes. And in Last.fm, nodes are users and links indicate friendships. Okay, so the first thing that we examine is the privacy accuracy trade-off of our method. For this, we basically vary the privacy budget we spend on features within 0.01, 0.1, 1, 2, 3, and infinity. And also we change the privacy budgets of labels in 1, 2, 3, and infinity. Infinity actually corresponds to the case where we do not do any perturbation. Here, we can see the accuracy of our LPGNN on test set on Facebook on the left and Last.fm on the right. As we see, the accuracy is quite stable as we decrease the feature privacy budget, especially on Facebook. For example, at the extremely low privacy budget of 0.01, the maximum accuracy loss is only around 10% on Facebook and 15% on Last.fm. But obviously, the model is more susceptible to the labeled noise. As we see, for a budget of 2 or more, the accuracy is very close to the non-private case on both data sets. But we notice like 5% accuracy loss when the label privacy budget becomes 1. So now we perform the same experiment, but this time with 2 different GNN architectures, GCN on the left and GAT, graph antenna networks, on the right. We see that GCN's behavior is quite like what we saw for GraphSage, but GAT is kind of robust only for feature privacy budgets of 1 or more. But in very high privacy regimes, when the budget goes below 1, we see a significant drop in GAT's accuracy. Actually, the reason is that GAT is more like a feature-dependent model, as it computes attention coefficients based on node features. But GCN and GraphSage mainly work with features in the aggregated form, and so they do not much rely on individual features. Okay, so it may come to mind that maybe node features are not really important in learning GNNs, at least for the GraphSage and GCN models that we saw were quite robust to the noisy features. So to verify this in practice, we basically compare our model in which the features usually actually come from the multi-bit mechanism, with 3 other kind of privacy-free features. I mean, some ad hoc features that are not privacy sensitive, namely all ones vectors, 1 hot degree vectors, where each node is represented by 1 hot vector, where actually the element corresponding to its degree is set to 1, and also totally random features. We see the accuracy of each method in this table. As we see, our method achieves a significantly better accuracy over all the data sets. So using some meaningful features, even privatized, has actually an added value. Okay, so now we compare our multi-bit mechanism with 2 standard privacy mechanisms, the Laplace mechanism and the Gaussian mechanism. We try different privacy budgets for features from 0.1 to 2. And you see the results in this table for 2 datasets, Quora and Facebook. We see that our multi-bit mechanism that only perturbs a subset of features could actually get a better accuracy compared to the Laplace and the Gaussian mechanisms in all cases. All right, so in the next experiment, we analyze how effective is KProp in improving the overall accuracy of our model. So as we have 2 different KProps, one for features and one for labels, we perform this experiment on both of them. The figure on the left shows the effect of feature KProp, and the one on the right corresponds to the label KProp. For both of them, we change the KProp step parameter K within 0, 2, 4, 8, and 16, and obtain the test accuracy for 3 different privacy budgets. Note that setting K to 0 means that we practically do not use KProp. So as we see in both cases, depending on the privacy budget, KProp could significantly boost accuracy. So for example, the feature KProp with K equals to 16 could get like 40% more accuracy with a feature privacy budget of 0.01. And also with label KProp at K equals to 8, we could get like more than 30% accuracy gain with a privacy budget of 0.5. Well, actually, with lower privacy budgets that correspond to more noise, the accuracy gain we get from KProp is actually higher. But for bigger privacy budgets, when we have less noise, this accuracy gain actually diminishes because of oversmoothing. Okay, so finally, we compare our drop algorithm for learning with noisy labels with 2 other baselines, the cross-entropy method, where we directly train the GNN with noisy labels, and also with the forward correction method, where we use the forward correction loss for training as well. We see that our method obtains significantly higher accuracies with different label privacy budgets compared to the other 2. All right, so we come to the end. So as a summary, we proposed a privacy-preserving GNN based on local differential privacy. Our contributions include designing the multi-bit mechanism for perturbing high-dimensional data. We also used KProp for both feature and label denoising. And finally, we proposed the drop algorithm for learning with privatized noisy labels. As we saw through the experiments, we found out that GNN models show a graceful accuracy privacy trade-off. Actually, we saw that for simpler models like GCNs, the accuracy loss is very negligible. So we can say that the feature privacy almost comes for free. And we also saw when we can get good accuracies with low privacy budgets for labels as well. Thank you so much for listening.